Let's keep the momentum going. Next up, we have a talk that will take us places. We are going to deep dive into in-car assistants. Our first tech talk of the day, going places with AI voice assistants. Right. Features Neela Sawant, Amazon. Neela Sawant is an AI practitioner with 20 plus years of R&D experience across diverse domains such as customer analytics, multimedia analytics including text, speech, image, video, and DevOps. Prior to Amazon, Neela has worked at Yahoo Labs, AT&T Labs, and has graduated from IIT Bombay and Penn State University. Let's welcome ma'am with a great round of applause.
Thank you so much.
All right.
Can you hear me? It's on. Can you hear me okay? Wonderful. Hi, good morning everyone. It's my great pleasure to be here, and thank you Wiz, and thank you all the organizers at Intuit for having me. It's a great platform, and I'm just so happy to see such bright faces and a full room. So thank you for attending. My name is Neela. I have been in the space of data science, machine learning. It has changed names over the course of 2 decades that I've been in this field. And I've gotten the opportunity to work on a lot of applied problems. So I've been part, within Amazon is more than 10 years now, and I've been part of their consumer business, AWS, and now I'm with Alexa Speech, which is now rolled into this AGI organization at Amazon. Over the time, the consistent theme that has remained for us is trying to use all the knowledge that we have to build a product that's useful for the customers, right? So it's always that situation that puts you into some very interesting challenges, right? And so you have to really think through, you may know a lot of algorithms and tools and techniques, but actually how do you actually combine all of that together to create something that's meaningful and useful, given all the constraints of the device, preferences of the users, and so on. That's the hard part, and that's also the most exciting part for me. So today, when I had the opportunity to speak with you, I thought, it's gonna be a tech talk. So let me talk about something that I'm working on, but also try to give you a flavor of all the types of machine learning algorithms or data science that can play a big role, right? Let's jump in right away. Okay, so the context is for in-car voice assistants. So most of us would be familiar with, Siri, Alexa, Google Assistants. These are on our phone, but now we are going to talk about what's in your car. And so a lot of the cars, some of the cars, I would say, like BMW, Stellantis, or Mahindra, they are actually trying to integrate voice assistant in cars. So there's going to be an assistant in the head unit of the car that is going to do something similar to what the voice assistants like Alexa and Siri do. In terms of the end-to-end system, what this looks like is that you basically have a system that takes a speech input. There's a ASR system, automatic speech recognition, that maps that speech into text. And there's another system for natural language understanding that tries to pass that text and try to understand the meaning of that text. And then it executes some actions downstream by using some on-device or cloud API calls. So just to kind of give you a flavor of what that means, I'll give you a few examples, right? So first, there are 4 speech signals. This is, what do you understand from this? We don't understand anything just by looking at the waveform, right? But we want this waveform, which is essentially the speech coming from our mouth, to execute something on device, right? So here are 4 different speech forms. And then the purpose of the automatic speech recognition unit is to convert that into text, right? So for example, in this, there are 4 examples. The first one would be open sunroof of your car, or it could be call a friend, or it could be playing music that you like, or it could be going someplace, right? And the fourth one, going places, that is actually something that I'll deep dive into later in the talk. So once you have the text transcription, the NLU unit will try to interpret that. What is the user's intent? Okay. So for open sunroof, it could be classifying that text into a car control intent with certain slot value. Opening is action, sunroof is the entity. Okay. Similarly, you have a contact intent, a music intent, and a navigation intent. And once this is kind of parsed, then you could make API calls either on device or on cloud. Now, as it so happens that a lot of some of these things are simple enough. Like for example, your car only has so many controls, or you may have only so many people in your phone book that can be preloaded onto device. And so controls and communications is something that can happen on device inside the car. Whereas when there are millions of music entries and millions of places to go, that is something that happens in cloud. So when we think of in-car voice assistants, there are kind of two modes of operation. There's a local voice control that does the simple on-device API calls, or there is cloud processing for the complex first-party or third-party API calls. And generally, the way this is done is that you will have a smaller model embedded into the head unit that's like millions of parameters. And for the complex ones, you will need to open up an internet connection, execute your cloud service to find out which is the song that you want to play, or is the place or like a map entity that you need to go to. Now, working in my company, we wanted to do something a little more. So basically, we wanted to check whether we could do navigation on device, and it's an extremely hard problem, given that like you just have like millions of entities. So the business problem that we had is, can you support navigation in a much smaller model that can be embedded on device? And this is extremely useful, especially in countries where you don't have good internet connectivity. You need to be able to find the place that you want to go to. You don't want your customers to be stranded. So the business problem was to make navigation applicable on device. And for scientists like us, basically when we translate web, that means that given a small model, you still want to do a good recognition of this. And if you look at think back on and map onto the training data, these are kind of like what we call tail entities, right? So they are not well represented in our training data sets, and so inherently your ASR systems don't do very well, and they need lots of bells and whistles to kind of pump up the performance, right? So when we started thinking about this problem, there were a lot of issues. First of all, we wanted to make this system in a small model, make it work for all kinds of auto manufacturers. And when we try to put something in a system that you don't personally own, right? It's something that BMW owns or Mahindra owns. You have these contracts where you cannot change the model for like a year down the line. So you have to take decisions that are 1 year in advance. And once you are kind of aligned with your partners on the system design, you can't really change much, right? So given all of this, we wanted to support navigation to a better extent. What I'll try to do today is kind of give you flavor of what can be done if you are in a situation where you have constraints like that, right? So we'll talk about three things. One is how we formulated the model. So here essentially we take like an ASR system, but then optimize it to this problem specific to cars, and especially for like taking cars to places that are ill represented in data. We'll talk about data issue as well in detail. So for example, a lot of times, you don't have for example, Alexa or some such systems, they have a lot of data from your on device, like devices that sit on the wall and listen to you at home, right? And their purpose is not really to take you places, right? It's just like for entertainment or some other in-house requirements, right? So the data is kind of, how do you match the data distributions? And finally, how do you optimize? So I work in ASR, but the ecosystems that I build are getting used downstream with other equipment manufacturers, with other catalog providers, and so on. So can we do something smart if we know what happens downstream? Can we optimize using that signal what we do today? Okay, so the first part, and yeah, so what does all this mean, right? Just to again make this concrete in our head, right? So if you have like that waveform that I earlier showed, incorrectly ASR may recognize it, right? So the first example is an actual incorrect recognition where it says, take me to Noah's Ark, whereas the correct text should have been take me to Noah's Art, which is actually happens to be a jewelry store in a certain location, right? So if I know that catalog, if I know my current location, and if I know that Noah's Art is like a local point of interest, then I can bias recognition towards a correct recognition. And similarly, the second one is where is nearest Little, and Little actually is a misrecognition for Lidl, which happens to be a massive chain of superstores in UK, right? So words like arc or little, they are very heavily present in our training data set, so it's very easy for the systems to get fooled. But if you do have like this knowledge of location, knowledge of catalogs, you can improve that. And that's what we are trying to do today. Okay, so the first of the three parts is the model formulation. Again, like ASR has been around for 20 years, even maybe more. And there is a lot of groundwork that has gone into building the systems that are today's, right? So just very quickly, the idea of taking some kind of a very long unsegmented series, input series, and mapping that to text. That kind of got traction around 2006 with this paper on CTC, connectionist temporal classification. And then in the last 8 to 10 years is just a massive explosion of ideas, starting with the transformers, followed by ideas of collecting pre-training and supervised fine-tuning, reinforcement learning from human feedback using multilingual data. So on the left side are some of the papers that you may find interesting if you want to dive deep a little bit. And on the right side is the second piece, which is what we also find very relevant, especially in the context of navigation in cars. And that is a use of location context. So the idea is rather simple. So let's say, actually, this happens to be a map of UK with like kind of 3 locations drawn on, but even here, right? So like we know like whether a person is in Bangalore or a Pune or Delhi, the type of places that is request are going to be geographically local, right? So if you kind of again use a location knowledge of location, that's going to be very helpful, and this is kind of supported in all of the literature that we've seen, even from the industrial setting. So we build on this related work, and we also take a system that's now published. It's also something that we put in on device for various automotive manufacturers. So let me try and explain to you. It's a system that takes an audio input and maps to text and actions. So on the at the bottom, you have an encoder network, and that's an audio encoder, right? So it takes an acoustic input and then maps into what are these yellow things, and that's kind of an intermediate representation of the audio. So you have 3 types of inputs going into the system. You have the audio input, you have a catalog encoder. So this is a catalog about places, maybe contacts that a user has, and so on. So this is like an additional information user has. And what you can do with that is shown on the right side, and this is like computing attention of what you're speaking with the additional contextual knowledge that you have. So the contextual knowledge could be, you could have like location, user information, their contacts, and so on. So you have a query, which is audio, and you have an entity, which is all this extraneous information, and you compute an attention, and comes out some kind of distribution over which of the catalog entities or which of the words are more likely given that information, right? So this is kind of the information. So you have encoder, catalog, encoder that compute biasing, and then comes the output is basically a probability y, which is just like the text. And because this is an autoregressive module, you could also use your previous predictions as an input to what you're going to predict next. And that is why you also have this prediction network where y u minus 1, which is like basically the previous audio input, right? So this is what a standard ASR system would look like on device. And what we did is we did some very simple manipulation, right? So we didn't want to change anything on the hardware, but we could add more inputs. So the first input that we added was the knowledge of a customer's location. And this is also a signal that that you can pass for your attention network. And then we also passed some POI catalogs, like some kind of catalogs over which we could compute attentions. All right. Okay. And what is the actual location? So location, if you think, is lat long, it's full precision, is very detailed. It could go, up to a meter long, but you really don't need that. And also the other issue is that geolocation is a very highly sensitive data. So a lot of times users will not give you permission. You cannot use the data as is in training. So we basically do some simple, clustering of the data. We try to find, given the occurrence distribution over certain geolocation, what are the right clusters? How do you actually, find the right number of clusters? And then once you have the kind of cluster centers, given any kind of input lat long, you could map that using a region mapping module to, and what comes out is on the right side, you have some kind of pseudo label for where the location is. It could be region number 1, region number 2, it could be a city, it could be Pune, Bangalore, whatever, right? So, but the idea is you want to do kind of a coarsification of that data and then use that as input. So that is one piece of, I hope that, kind of falling in place, right? So we have a model, we pass one input, and then we also pass another input, which is catalogs. Now, on device is a very small memory, right? So you may have, your places could be in millions, right? In Bangalore, Pune alone, how many places each of us would go to, right? Well, just a huge number. But we don't really want to keep all of that in memory, because a lot of that information your ASR models will know offhand, like words like little, like some common words. You don't need to store them. The model, like Starbucks, for example, could be very heavily populated in the data. So you don't really need to do an additional bias or compute additional attention over it. So you need to filter it down, right? And so we basically started with a very large catalogs, but then we said, okay, I just want to give, for each region, I just want some unique places where ASR doesn't do well. And so we basically do a TF-IDF based scoring, and then what we have like an initial set of entries. And then we also try to see which of those entries ASR gets wrong. So we would, let's say text prompt is little, we do a text to speech, and then we run our ASR and see whether that entity was recognized correctly. In this case, little was recognized as little. So that is something that we know that we do need to bias towards, right? So if it is correctly recognized, we discard it. If it is incorrect, obviously we use it. And so we created a small catalog, and we do that for different regions. So some of the example recognitions would be, for example, in the first, let's say the second case, right, which we already talked about, where is Noah's Ark, and the ground truth annotation is Noah's Ark. And we actually see that, some of these catalogs for matching POIs could be selected if that's like a uniquely popular entity in that region, right? So some of that will come. So Ark, or Noah, words like that will come into your biasing. And yeah, I mean, this is just a simple ablation study. I don't think, the numbers, absolute numbers would make any sense, but what you want to do that is that, a lot of times ASR system will not work out of the box. You do like a lot of trial and error and see which one works best. So in our case, we do see certain improvement, both from just location-based biasing, passing that as an input to the encoder, as well as using the catalog. So, and that seems to happen across all types of places that we're interested in, like street name, places, city names, and so on and so forth. So that's the first piece. And the second piece I wanted to talk about briefly was around data augmentation. So we have model, and model needs data, right? Again, a lot of data, there could be a dearth of, like a lack of data. So for us, we have, our data comes from disparate sources. So we have data that comes from your like how in-house devices or car devices, or we could just have catalogs, right? So there is no audio, but there's just speech. So the data happens to be a pair, for most part, it's a paired audio text based on some kind of ground truth annotations. And we have a system which will basically kind of try to figure out the right mix of the different data sources based on its evaluation on some development set. So there's one thing I'm sure like a lot of y'all are doing anyway. One trick that we started looking at is using LLMs to kind of like boost the synthetic data into our models. So, for example, you have like Yelp data, you have some other kind of catalogs, right? So the catalogs will have textual entries like names of places, geolocation, and so on. And so we ask an LLM to kind of come up with prompts, right? This is something like different ways of how a user might ask their car to go to a place, and the LLM would take as input like your catalog, and it would do whatever normalization that needs to happen, right? You know, sometimes your address, especially in India, ill formatted. But if you do like some kind of like a few short prompting, you could get it to work so that, you know, somewhat reasonable utterances can come out. So we do use like some amount of LLMs to generate our synthetic data and then use that for to augment our data set. So this is one piece, just getting general data. The second piece I think was interesting for us especially was getting location information. So location in general is a very sensitive, I mentioned that, right? So it's privacy, has privacy concerns. You don't want to use a lot of the data we cannot store. If it is stored, it has to be deleted within certain days, and so on and so forth. And so generally, when your model training cycles are going to run for many months or many weeks, and the data gets deleted in a matter of days, that's not like something you want to be in a situation of. So so the one idea that we started thinking about is to how do we impute reasonable features or interesting features, and so we kind of flipped the problem. So we said, okay, we call this as a locality hypothesis. Like if a person is in Mumbai, he's going to ask for Mumbai POIs. But if I observe two people, okay, and if I see that one person is consistently making requests for Mumbai POIs versus Bangalore POIs, then we kind of say something about where they are, right? So here we actually used like a Bayesian formulation to understand what the user queries were. So in the beginning, you have this kind of like a blue, and let's say there are two cities, right? Red and blue cities. Initially, you have like an uninformative prior where the user is coming from. You don't know anything, but then you start observing some interactions, and you kind of, you know, shift your posterior to the more likely beliefs. Hey, you know, I think my user is in Pune or my user is in Mumbai, and then you kind of use this kind of exploration exploitation, and then try to figure out where they are, and that becomes your feature. Right? So you don't have anything which is privacy sensitive, but you can use this very well because that interaction is kind of in your domain and it's approved. So we use this as a feature as well. So I talked about formulation, I talked about ways to get model like data, and then the final third piece I have is the model optimization, right? So yes, you given the data, given a model, you can absolutely build an ASR system, right? But that's not the end of it, because the ASR system needs to be used somewhere. It needs to be used by somebody who interprets what that text means, right? And actually call the on-device APIs. So here we started with also something that we firmly believed in, that, you know, we don't want to stop at just optimizing ASR system for word error rate, which is like the traditional metric, but we believe that not all of these errors are important, right? Only those errors are important that are going to cause a problem for the user. So if you let's say if you have this utterance "bye bye baby," right? I give an example. Now "bye bye baby" can mean music, or it can be a place in US, right? It's a store. Um, or you know, you could have some lexically similar words like den or dining. When a user speaks, they might, you know, sound, you might hear them similarly, but they might actually mean different things. So we wanted to ensure that we are kind of optimizing for the right complexity. If something is if the downstream error, if ASR makes errors, but then downstream system can recover from the errors, we don't care about that. So we try to bring in some kind of optimization that takes into account what happens towards the end. And so for this, we tried incorporating a catalog loss, because eventually we wanted, for this navigation, what we care is whether the place is in the catalog and is correctly recognized. So in terms of like the earlier image that I showed, to at the top of it, when we compute ASR losses, we also compute something that is used for downstream. And here is specifically what we used is what it's trying to show is a triplet loss, like just as a motivation, right? So you have three entries. You have A, P, and N. A is your anchor, which is the audio you speak. P is the positive entity, which is the correct recognition. N is the negative, which is the incorrect recognition. And what you want to learn is an embedding space where your A, P, N could be distributed somehow, but through the learning process, A and P, which are those two blue points, they come together, and N is pushed apart, right? And this is the triplet loss formulation. People have tried many different complicated formulations like constellation loss and so on and so forth. So this also helps quite a bit. And this is also one of the published contributions from my team. So we tried sampling. You can now this is where data science could also help, like because you know your domain, you know what are similarities you care about. So you can sample your positives, negatives in any space, which space that makes sense to you. It could be lexical or otherwise, or phonetic or something like that. So we tried a bunch of techniques, and then we figured out, we ran a few ablations and figured out what worked for us. And this also went as a very meaningful contribution towards making our systems capable for on-device navigation. So yeah, so I think I'm doing reasonably well in terms of time. On the last slide, what I wanted to show today is we are all of us are builders. We build systems that are useful for customers, and these systems have to work in a very constrained atmosphere. You have constraints on the system, on the data, and the type of compute that you have. But you do have, fortunately, a lot of interesting techniques out there that you need to understand and cook your meal. And that's exactly what that excites me. So here I've talked of a bunch of things in the context of in-car voice assistants, and I'm happy to take questions and talk about any other topics of interest. I'm here now and also throughout the day, so feel free to ask me questions. Thanks again. Yeah, yeah, I think she's and then I'll take it. Yeah. You want to use the mic?
Thank you. Hi, that was an interesting talk. First of all, thank you for that. If I want to deep dive in catalog encoder and also catalog losses, sensitive losses, any reference or paper material that you would?
Yeah, I have a bunch towards the end. I'm happy to share the slides also.
Perfect.
Yeah.
Thank you. That's all I have.
One question in this one of your slides, you mentioned like you are working for training any sort of data, especially in the geographical location, as it cannot be available easily. So you are training that data on a goal level only directly, like as like suppose you are in a car system. So once you implement it, then I am driving. That time only you get to know like now I'm in Pune or in Bangalore. So like on a go only you'll do that.
Yeah. So we do have like the concept of training and inference. So for training data, we do have that information from Atene. But for inference, so there is two things. Yeah, the geolocation information comes on device on the go. So it's at runtime that we compute the inference. The other thing, yeah, there are also like other optimization. Your location doesn't change dramatically, right? So you could do like smart computing and so on. So forth. Yeah.
Thank you.
Yes.
We'll take one from there and then I'll hand over.
Yeah, hi ma'am, very interesting talk. So I have one question, which is while doing a pre-processing in natural language processing, we tend to lose a lot of data. So here you are taking a text speech and then converting a text, and again finally that text has to be encoded. So there must be some loss of data. So how do you recover from that loss?
Yeah, so I think, I mean, it depends on the application. So we are not in the business of speech generation. So there is no like reconstruction loss that we really care about. We care about semantic losses. And so in speech and in text also there is a lot of redundancy, right? And so it is less affected, like the speech understanding is less affected by the loss of information than speech generation. So I'm happy to chat further. Yeah.
One more question. Sorry.
No.
Yeah. So I'm from a CMR Institute of Technology, and because of the AI and all these things, there are a lot of technologies are becoming disruptive. So I want your suggestion or your take, like for early graduates, what are the things that you will be looking at, like the key skills or the key areas?
Yeah.
Thank
It's
you.
a good question. I cannot give you a very short answer. I'll try. I think more the couple of things. There's a disruption has happened. All of the students, all of the professionals have access to world-class material. Right? You have even like notebooks and stuff. You have data and you can actually do a lot of hands-on work. And so I do see a lot of people who are very excited, who try something and they have results, they get excited. For me personally, I also do care about the foundations. So I do care about classical machine learning as much as I care about deep learning. A lot of the work that I showed today, we are doing that is in deep learning, but the ideas of that have come over the past 20 years. And unless we understand the foundations of even like going back to like causal inference, like some very classical methods, you'll not be able to create differentiation for you, because right now everybody has the same tools. To be able to make further differentiation, you do have to be really strong in some of those basics. That's what I would say. Good.
Ma'am, we have a question here.
Okay. Yeah, it's also break, so I'm happy to I don't want to eat into people's break. But I'm happy to take as many questions as I can. Yeah. So up to you. Right?
One question. Yeah, we can have one more question.
Yeah,
and then
this lady
there's
was
also a
here
break coming
Yeah,
up
so
where you can. There's also a networking session later on as part of lunch. You could also connect with all of the people here. Yeah.
Like as you have mentioned that you are already using LLM for data augmentation. So just curious about though the system which you people have built might be you people might be building from very like from the scratch, and it's long time work, but wanted to understand that you people have actually been evolved, let's say using LLM at the back end. So my understanding is that is more towards internal and nothing to deal with the end user, right? So in the entire system, are you also using GenAI anywhere else than at the internal use?
Yeah. So first of all, I think this is a case for all of the companies, and all of the companies have built their tech stack over many years. And LLM is something that's fairly new. So people kind of are in this hybrid situation where they're trying to maintain both for the best of the use cases. So we do have, like, for example, in case of speech, we have text to speech is one very good application. We want your voice assistant to naturally interact with you. So it should understand your the tone, the intent, and all that. It should not be very mechanical. So we do have like a lot of work in Gen AI in terms of like generating synthetic data and then also translating that data into like speech back to the user. Right. So that's actually part B. So speech understanding is part A of our systems, and text to speech is part B, where we use a lot of Gen AI.
So the
And also, like, sorry, I'll just, and I only talked about speech, but all of our systems are multimodal now, so it can take your like a video input, it can take the text screen input, and so on and so forth. Yeah.
And the reason of asking this is because the companies which are actually being heavily involved in GenAI, one of the major problem which they are facing is cost and scalability, right? Because if a user themselves, if like let's say Amazon or the company which we work on have a million or billions of user, which is making let's say n number of calls in a day, right? Whatever we have built, how we are actually making it scalable and how we are maintaining the cost.
That's precisely why the stock is important, because we're trying to do it on device for the user and try to minimize the cost to cloud, right? So scale, and that's you don't want to use a very large system for something that can be done simply. So you, as scientists, it's on us. Like, we figure out what's the right way to use it, and if you can show that you can be efficient and cost effective, it's a great starter for your career.
Yeah, thank you.
Thank you.
Thank
It's
you
my
very much,
pleasure.
ma'am.
Really, thank
We
you.
have a token of appreciation. May I request Hitendra, our senior staff data scientist, sorry, to present this token of appreciation.
Thank you so much. Okay.